So what we're going to do today is a sort of rehearsal of what you are to be doing in your hostel rooms. So there are recorded lectures, and in today's class and probably also in the next class, we're going to play the recorded lectures in classroom and then discussion. Where subsequently you are supposed to view these recorded lectures in your hostel rooms, and we will only work with problems. We'll discuss problems and whatever doubts you have.
Hello and welcome. This lecture is about a simple computer's architecture. Here is a quick recap of some relevant topics that we have already discussed earlier. We have discussed the Dumbo model of computing, in which we have seen that there are named drawers for storing values and retrieving values from. There are some workbench registers which Dumbo uses for doing computation, and Dumbo also uses carts to do input and output when we instruct Dumbo to do some input or output operation. In this lecture, we are actually going to see a little bit in detail what is it that we will actually be programming. Essentially, from the Dumbo model of computer, we are going to move towards a real computer, which by the way is almost like a Dumbo. We'll see a lot of similarities between what we have seen for Dumbo and what a real computer contains. But we would like to see what this real computer is, what are its different parts, what are its architecture, what do the different parts do, and how is information represented inside a real computer. So that is our agenda for this lecture. So here is a very high level block diagram of a simple real computer. I am going to explain each of these color coded parts in more detail, but just to get going, here is something that I have labeled as main memory, and in it I have put these labels location 0, location 1, location 2 and so on. Now these are like Dumbo's drawers. Remember that Dumbo needs named drawers to store information and also to retrieve information. So this main memory in a real computer is much like Dumbo's drawers. Then recall that Dumbo had a workbench in which Dumbo would keep values and then do some operations with them. Dumbo would fetch values from the named drawers to the workbench and then do some operations with them. So in a real computer, that part is what is called a central processing unit or a CPU. A CPU has several registers. In the Dumbo model as well, we had seen registers. We will study a little bit more about what registers really do. A CPU also has an arithmetic and logic unit where the real computation happens, and it has a controller. Now Dumbo also shipped information from one part to another, for example from the named drawers to the workbench or from the named drawers to the input or output devices by means of some carts. Now in a real computer, the analog of these carts are what are called buses. So here you can see I have written a bus, and on this bus there are disks, input devices, output devices. Here are some other buses which is called an address bus and a data bus, and these also transfer information between different parts of a real computer. So having seen the similarity between the Dumbo model of computation and what a real computer looks like inside, let us go a little bit more in detail into each of these parts. Here I have highlighted the main memory that we just mentioned. Now this main memory is usually also called random access memory or RAM, or it may simply be called memory. Basically it contains a large number of addressable locations, just like Dumbo's chest of drawers had a large number of named drawers. Each location in main memory stores exactly one value at a time. What is very important to remember is that even if you did not store a value at a location of memory, there is some garbage value already there. So every location in memory at every point of time has a value. If you stored it, then it contains the value that you stored. If your program stored it, then it contains the value that the program stored. Otherwise, it contains some arbitrary garbage value. So when you are accessing a location in a memory, you should be prepared to encounter garbage values if you have not already saved something, or if your computation has not already saved something there. This is very important when you get to real programs. Now writing to a memory location destroys the value that was originally there. However, reading from a location makes a copy, it does not destroy the value that was there. Note that these are exactly how Dumbo's drawers also operate. Let us now focus on another part of a computer, which is the set of registers or the bank of registers. Now registers are pretty much like main memory, except that they are much faster. You can read and write from registers much faster than you can do from main memory, and of course you pay a price for it. They are much more costlier. To design maybe 32 registers, you may have to use the same amount of resources as to design maybe 1,000 locations in memory. So that is why registers are much costlier, and because they are costlier, they are usually present in smaller numbers, which means you have fewer registers than you have locations in main memory. Now for most of the programs that we are going to study in this course, we will not directly see these registers, although of course these registers are going to work behind the scenes. The real computation happens in the central processing unit by taking values from registers and storing values back in registers. However, in our programs we are not going to see too much of these registers. Nevertheless, it is important to remember that advanced programming can refer to registers directly. We will not cover this in this course. Now here I have tried to highlight two other parts of the computer, the arithmetic and logic unit and a controller, which are also parts of the central processing unit. The arithmetic logic unit is really the workhorse of the computer. All the arithmetic operations like addition, multiplication, division, subtraction, and also all logical operations like logical ANDing, ORing, XORing, complementing, all of these happen here. The arithmetic logic unit usually takes operands from registers and stores the result back in registers. The controller, if you see, the controller here has some arrows going to the registers and the arithmetic logic unit. So the controller is responsible for sequencing various actions that are involved in executing instructions on the computer. We are not going to directly see this controller as we write programs to execute on a computer. Nevertheless, this controller plays a very central role in the functioning of a computer. In this picture, I have highlighted the disk and some input devices and output devices which are connected on the bus. Disks are basically longer term storage for files, and files could contain your programs, could contain some data, it could contain some logs, some outputs and so on. Now disks serve the purpose much like main memory. They are used for storing information and retrieving information. However, they are much slower than main memory. They also have much larger capacity, many more locations than main memory, and they are also significantly cheaper than main memory. So as you can see in this picture, there is main memory and then there is this register file which is faster, smaller and costlier, and then there is this disk which is slower, larger and cheaper than main memory. Now we are going to look at disks much more later on when we study about files. Input output devices, also called IO devices, these basically allow a computer to interact with the world outside. For our purposes, an input device is going to be a keyboard, an output device is going to be a console, although computers can interact with a lot of other kinds of IO devices. Finally, I want to highlight the buses. Here there is an address bus, data bus, and this is a bus on which the disk and input output devices are connected. The buses are really the highways for transferring information between different parts of a computer. In the Dumbo model, Dumbo would transfer information using carts. In a real computer, buses serve that purpose. We can have different kinds of buses like address buses, in which addresses for specifying locations of memory are sent, data buses through which data may be shipped between a memory and the central processing unit, IO buses through which data information could be transferred between IO devices and the computer, external device buses, for example, all of you are familiar with USB, which is basically a bus, the universal serial bus. For our purposes, as we write programs, we are not explicitly going to see buses, they are going to be working behind the scenes, nevertheless they are an important part of the computer. Now how is information represented in a computer? All information in a computer is represented as sequences of zeros and ones. So if you were to take a snapshot of the computer that we just saw, it would probably look something like this, that there is main memory and there are sequences of zeros and ones stored in various locations. On the address bus and on the data bus there are sequences of zeros and ones, and everywhere it is basically sequences of zeros and ones. Now why is it that computers talk only in the language of zeros and ones? Because electronic circuits in the computer can efficiently store and process electrical signals in one of two states. For our purposes we call them 0 and 1, and therefore all information in a computer is basically going to be represented as 0 and 1. So this is also called a binary representation, and these two binary digits are also called bits. Information is usually accessed in a computer not in terms of individual bits but in chunks of 8 bits, which is also called a byte. So for example, when we access memory, IO device, register, or when we send an address, we usually send chunks of 8 bits. And it is very important to understand how numbers, characters, strings, the different kinds of things that a computer is going to process that we will write programs to manipulate are represented using bits and bytes, but this will be the topic of another lecture. So in summary, what we saw in this lecture is the architecture of a simple but real computer. The main parts are a main memory, registers, an arithmetic logic unit, input output devices, disk, bus, and of course there is also a controller which along with the arithmetic logic unit constitutes the central processing unit. We have also seen that information is represented in a computer using zeros and ones, which are called bits, and we access bits in chunks of 8 bits at a time, which are also called bytes. Thank you.
So this is how a lecture module is going to look like. This is roughly 13 or 14 minutes, and it will discuss one subtopic. Here it was the basic architecture of a computer. You can rewind it and see whichever part you did not understand, but basically in a couple of classes from now we will not be playing these lectures over here. You are supposed to be seeing these in your hostel rooms before coming here. What we will be doing mostly in the classroom is what we are going to do now. You have seen a lecture and now we are going to have some discussion. We are going to try to solve some problems, answer some questions. Okay. So was there any doubt about what you saw so far? No? So here is a question that I'd like you to think about an answer. So we've seen how a computer looks like. This is main memory, ALU, buses, disks, and all of that. And of course this entire course is about programming a computer. So we're going to run programs on a computer. The question is, when a computer is running a program, where does the program reside? Is the question clear? Right? So you think of the Dumbo model of a computer. So Dumbo executing a program means whatever, it's opening drawers, taking out things, taking to the workbench and so on. But of course Dumbo needs some instructions and it's just following those instructions. And the question is, where are those instructions? Okay. So the way I would like you to answer this question is that on your notebook, please write down what you think is the correct answer. You've written down. So now please swap it with your neighbor and see whether your neighbor agrees with what you have said. And if there is disagreement, in low decibels, try to convince each other whether you are correct or your neighbor is correct. And if there is agreement, then at least try to say why you think you wrote a particular answer, and your neighbor can say why he or she thought the same answer. So I mean, this is a simple question. So I hope you have convinced your neighbor, or your neighbor has convinced you about the correct answer. So now let me ask, how many of you are now convinced after discussions with your neighbors that the program resides in registers? Please raise your hands. Okay. But your neighbor doesn't agree with you, is it? Oh, okay. So some other people who said registers, yeah, registers, please raise your hands, those who answered register, okay. And your neighbor doesn't agree with you, is it? Because I don't see pairs of hands going up. So let me ask your neighbor why he doesn't agree.
I think that main memory should be done.
No, but why is register not the answer? Okay, so why do you think register is the answer?
Because I think that it will, while executing the program, the computer will store that program in something like temporary, for temporary storage, it will put in the register.
But not in the main memory, I mean.
No, not while executing the program. Otherwise it will stay in the main memory, but while executing it will have to compile it and put it somewhere.
Okay, so he thinks that the program has to be stored in the register. Okay, now what about main memory? How many of you think it's main memory? 50% of the class. And how many of you think it's the disk? Few people. And IO devices, anybody? Nobody, okay. So IO devices is out of our consideration. Now among those who said main memory, can you please raise your hands again? Yeah. So, you know, the point of this discussion is, I mean, even if your answer is correct, the reason why you're saying that answer may not be correct. And what we'd like to, I mean, more than the answer, this discussion is about trying to figure out why it is the answer and why something else is not the answer. Right. So, I mean, you said a lot of things in favor of main memory, but you didn't say why anything against registers or anything against disks. Okay. So that's an interesting answer. The disk is too slow and the registers are too small, so the main memory is somewhere in between. Okay. Anybody else?
To decide in the main memory, because when we give some input for the execution of a data, it will first of all it will be stored in the main memory, then it will be copied from there. So one copy will actually remain in the main memory and the other will be executed on the register side.
Oh, so part of it is in main memory, part of it is in registers. That's what you think. So you would tick both registers and main memory from here.
One part will reside in the main memory, and the other execution will be done at the register.
At the registers.
The workplace.
Okay, so you're basically saying both registers and main memory, right? Part of it is in register.
Yeah.
Okay. Yes. Oh, there's somebody from there. Yes. So which do you think? What are you arguing for or against?
So I'm for main memory, because I think because main memory always creates a copy of that thing, and registers once we do something or calculate, it just goes away. Means it's kind of temporary memory, as we saw it from the Dumbo model. And main memory always creates a copy. So whenever we want to execute, we can execute. But register again.
So when main memory creates a copy when you read from the main memory, that's what you mean, right?
Yes.
So from the register also, when you read,
we'll
the
have
value
to
stays
again
in the
perform
register.
it, right?
So if you look back at the, so these are the slides. So, for the registers, they are just faster, costlier, smaller versions of main memory. So the other than that, they are the same.
We couldn't store anything in the register.
Pardon me?
We could not store anything in the register.
Why is it? I mean, we can store. I mean, they are just like, it's just that they're faster and there are fewer registers than main memory. So other than that, when you read something, a copy will be made. When you write something, the previous value gets destroyed. So other than that, it's almost the same as the main memory.
So
yes?
main memory has got large number of addressable locations, and each location stores a particular value. So it's very easy for Dumbo to work with the main memory. Besides, registers work too slow and they have a very limited memory. So it will be very difficult to work with registers, and disk, if it works with the disk, it will again be very slow. So I think it should be main memory.
Okay, so that's very nice. Yeah, so I'm sure there are other people who want to add to that, but in the interests of time, I think we can continue the discussion. So in the interests of time, so the right answer is indeed main memory, but more important than the right answer is the reason why main memory is the best place to keep it. And as some of you have already pointed out, so I'm very happy that this came out in the discussion in the class. Is that a program typically will be, have you heard about, so for example, a banking application, do you have any idea of how many lines of code it is, or any industrial application, let us say, an airlines ticketing application? So any idea of how many lines of, let us say, C or C++ or Java code would it be? 10 lines? Or the Windows operating system or the Ubuntu operating system, how many lines of code is it? That's a program, right? An operating system is a program, it's running. Yeah. Lakhs and lakhs of lines. So yeah, so it's a very large amount of, a program is actually a very large amount of information. So if you want to store it in registers, it won't fit in your registers, right? So some of you already said that registers are too small, too fewer. Now what about the disk? The disk is, of course, it's much larger than main memory. You can store whatever you want over there. But then these are very slow, right? So, oftentimes, you can see in your computer or laptop, you ask it to read a big file and you can sort of hear the disk spinning, some kar sound happening, right? The disk platters are spinning. And it takes time to access that. So have any of you sort of run a computer which is running on solid state device memory, SSD memory? Yeah? No? Okay. Anybody who has a tablet, an iPad or something? So, okay. So there are different kinds of memory. There are different kinds of disks also these days. There are SSD disks. And what you would see immediately is that the time it takes to access data from disk, whether to read or to write, is significantly more than the time it takes to access data from main memory. So a program is roughly about the size that is okay for the main memory, and we also want to access it fast enough. We don't want too much time to get one instruction after another. So the main memory is kind of the right place for it. Okay, so it's good that this came out in the discussion from the class. Now, a related question that now that we have discussed main memory registers and disks is, why not just work with disks, right? So, of course, we've just discussed that if the program were to recite only on disks, it would take a long amount of time. But then one might ask, okay, then maybe main memory and disks. Why do we need registers at all? Right? If you remember, all three of them, main memory, registers and disks, are for reading and writing information. Registers are smaller, faster, costlier. Disks are slower, larger, cheaper. And main memory is somewhere in between. So it's kind of like a hierarchy there. So the question is, why do we need all three of them? So once again, you can write down in your notebook a couple of lines, and then after that we'll exchange it with your neighbor. So let me pick somebody at random.
The program stored in the main memory will be erased later on if another program is stored in that, So we have to use disk to store the program. As the registers are very small, so we have to use the disks in place of registers and the main memory. And to do the programs faster, disks are not useful. So we have to use the register rather than main memory.
Okay, so it's more or less the same answer. Yes, over here.
So we need this because sometimes we need to store programs for further usage and all, and like RAM is like the main memory is temporary, like we also said earlier. And so we will be needing our disk. And for sometimes the programs are far large to get us. Registers are needed to quickly do the calculations for the short term, and then it does not need to remember all the calculation process, it just needs to know the final value. So maybe registers are needed so that it can calculate and reduce the load of the main memory, and then only the final value can be stored in the memory. And the main memory is needed for the regular processing or execution and comparison and everything of the program, and to
Okay, so you're saying what the three different things are to be used for. Okay, okay, good. So I mean, ideally, what we'd like to do is we'd like to have fast memory and cheap memory and a lot of memory, right? We would like to have the fastest, cheapest, and highest capacity. And if somebody could give that to us, we wouldn't need all three, right? Unfortunately, today's technology is such that we don't have all the three together. If you try to make something fast, it becomes costlier, right? If you try to increase some, if you try to make a large fast memory, it will be really, really expensive. So, these are at sort of the three levels of a hierarchy. As we have discussed in the lecture. Disks are slower, but they're much larger and cheaper. Main memory is faster, much faster than the disks, but they're also much smaller because they're more costlier than disks. And registers are even more costlier, even faster, and therefore they're even smaller. So it's kind of like an engineering optimization problem, right? I would like to have the best of all worlds, right? I want the same price as I pay for disks, but I want the same speed as I get for registers. So therefore I have to organize things appropriately, things which I do not need right now for my computation can stay in the less expensive part, which is the disk, because that's what I don't need for computation. Things which I really need for my computation, I want high speed, that should be in the registers. And the main memory is, of course, as somebody pointed out, it has large enough number of locations that most programs would fit there, but the speed is still not as high enough to match the speed of the ALU. I mean, if we could make main memory fast enough to match the speed of if the main memory just became a huge bank of registers, probably we wouldn't need registers, but that machine would become very, very expensive. Okay. So it's really, they serve three different purposes, and somebody also pointed out disks serve the purpose of more permanent storage, right? You write some data there, and certainly magnetic disks are much more, more permanent storage, and these days we have solid state disks. They are also much more permanent storage. So these three things actually serve three different purposes. So while one could think of a hypothetical computer which runs only on disks or only on registers, you would be sacrificing, if you run only on disks, you have to sacrifice on speed. If you run only on registers, you have to sacrifice on cost, right? It will become very expensive. So this is a kind of an engineering optimization problem where you want to get speed and also reduce the cost, and so you maintain it in this way, okay? The part that you're really computing it, you want it in the fastest memory. The part that you're not computing can stay in the slower memory. The part that you need much later, why keep it in the fastest memory? Let it stay in the slow memory, right? And as we said, in main memory, the program also stays because we do want to access the program at a speed that is faster than accessing disks. And so there is a separate part of main memory where the program will reside. The data will be in another part of the main memory, and they're not going to interfere with each other. Okay, good. So now what we're going to do is we're going to proceed further. Subtopic. What we will do is we will start the second lecture module. So this is again, around 13-14 minutes. And once again, so now you know the way we're going to conduct the class. You're supposed to see the lecture, and then there will be questions. Some of these questions may be simple, some of these may be thought-provoking, some of these may not have one unique answer, but we're basically going to have that discussion in the class, okay?
This lecture is about how computers internally represent integers. Here is a quick recap of some relevant topics we have already studied. We have seen the architecture of a simple computer, and we have also seen that information is stored in terms of binary digits or bits, which are usually grouped in chunks of 8 called bytes. In this lecture, we are going to study how numbers, and specifically how integers, are represented inside a computer, and we are also going to see how in a C++ program we can declare integer variables. Now, from the earlier lecture, you would recall that a snapshot of our simple computer looks like this, where we have different parts of the computer, and in each part we basically have sequences of zeros and ones. So the question is, in such a setting, how do we represent integers like 56 or minus 37 in terms of zeros and ones inside a computer? Now when we talk of representing integers, the most natural thing that comes to mind is a decimal representation with which all of us are aware. So for example, when I write a decimal number like 233, I am really using base 10, which basically means that to interpret this number, I take 2 and multiply it by a power of 10, in this case 10 squared, then I take 3 multiplied by a power of 10, in this case 10 raised to 1, this 3 is multiplied by 10 raised to 0, and I add all of them to get the value of this decimal representation of the number. So we call it base 10 because this number, which we are raising to various powers and multiplying it with the digits here, is 10, and in base 10 representation the digits that we need are from 0 to 9. Now there is nothing very special about a decimal representation. We could also do this using base 2, in which case we will call it a binary representation. And just like in base 10 we need numbers from 0 to 9 to represent an integer, in base 2 we need numbers from 0 to 1, which is 1 less than whatever the base is, to represent an integer. So here is a binary number 110, please do not mistake this as 110, it would be 110 in decimal representation, but in binary representation it is 110, and let us see what this number really represents, what 110 represents. So just like in the decimal representation, I have got to take the numbers that are appearing here, multiply them by an appropriate power of 2, the base is 2 here, and then add them up to get the number represented over here. So for example, here it is 1 into 2 squared plus another 1 times 2 raised to 1 plus 0 times 2 raised to 0, or 6. So this is the binary representation of the number 6. And if you understood how I interpreted this sequence of zeros and ones as an integer, you would realize that any sequence of zeros and ones can be thought of as representing an integer. Now that we know how to represent numbers in both binary and decimal notation, how do we go from one to the other? So for example, I could ask you, given this binary number, I am going to denote binary numbers in green and decimal numbers in violet. So given this binary number, what is its decimal counterpart? So the first thing to note here is that this binary number has 4 bits. So this bit is going to be associated with 2 raised to 0, this with 2 raised to 1, this with 2 raised to 2, and this with 2 raised to 3. So the maximum power of 2 that we are going to use is 3, that is the number of bits minus 1. And then how do we figure out what integer this is in the decimal notation? We take this number, start with the bits and keep multiplying them by the appropriate powers of 2. So this is 1 multiplied by 2 raised to 3 plus 0 multiplied by 2 raised to 2 plus another 1 multiplied by 2 raised to 1 and the final 1 multiplied by 2 raised to 0, and that gives us the number 11. Note that in this representation, which is the decimal representation of the number 11, I am also using the digits 1 and 1. This is the binary representation of the same number 11, in which I am also using the numbers 1 and 0. However, this representation is very different from this representation. This is a base 10 decimal representation, this is a base 2 binary representation of the same number 11. So if you look at 1011, this bit which is associated with the highest power of 2 is called the most significant bit, or MSB. This bit which is associated with the least power of 2, which is always 2 raised to 0, is called the least significant bit, or LSB. So we saw how to convert a binary number to a decimal number. Let us see how we might convert a decimal number to a binary number. So given 23 written in decimal, what is its binary counterpart? So the way we are going to do this is, since we are interested in binary numbers, we are going to repeatedly divide this number by 2 and collect all the remainders as we go. So I first divide 23 by 2, I get a quotient of 11 and a remainder of 1, and we will see that this remainder of 1 will be our least significant bit in the binary representation of 23. Now what does this mean that 23 divided by 2 gave me a quotient of 11 and remainder of 1? It really means that 23 can be expressed as the quotient times the divider, 11 times 2 plus the remainder. Now what do we do with this quotient 11? We repeatedly divide it by 2 again and we get a quotient of 5 and a remainder of 1, and now I could express 11 as 5 times 2 plus 1, and if I did that, in place of this 11, if I substituted 5 times 2 plus 1, I would get this expansion of 23, and if I expanded out further, I would get this representation. And here you see now that this one corresponds to the least significant bit, which is 1, this one corresponds to the next significant bit, which is another 1, and I could keep doing this. I could take 5 divided by 2, get a quotient of 2, remainder of 1, then express 5 as 2 times 2 plus 1, just as I have done here, and that way I get this representation of 23, which actually gives me the next remainder. And finally I take the quotient here, which is 2, divided by 2 again, get a quotient of 1, remainder of 0, and now if I express this 2 as 1 times 2 plus 0, this is the expansion of 23 I get, which finally gives rise to this expansion of 23. Now where do I stop? I will continue until I get a quotient of 0, so I divide 1 with 2, get a quotient of 0, and it is only then that I stop, I get a remainder of 1, and this becomes my most significant bit. So as you have seen that we took the decimal number 23, repeatedly divided it by 2, kept collecting the remainders in order from the least significant bit to the most significant bit, and that gives us the answer 10111 as the binary representation for the decimal number 23.
Here what we discussed, how to represent unsigned numbers in binary. So now what I am going to do is, I am going to ask you to answer this question. If I give 101010 and I ask you what is it as an unsigned integer, please write down in your notebook. Okay, now swap your notebooks with your neighbor and just see. I think for most of you this probably will not require any discussion at all. Most of you would agree what the number is. Okay, so no discussion, no argument, nothing. So this is 42. Essentially this is 0 into 2 raised to 0, that's 0 into 1, that's 0. This is 1 into 2 raised to 1. So it is 2 from here, then 8 from here, and 32, right? So 32 plus 2 plus 8, that is 42. So now what we'll do is, we'll see, I mean in a computer when you're working with numbers, it's not just unsigned numbers or positive numbers that you want to deal with, you also want to deal with negative numbers. So let's see how we're going to represent negative numbers. In particular, now we are going to deal both with positive and negative numbers, so we call these signed integers, and let's see.
Now so far we have talked about representing unsigned integers. So how do we represent signed integers like -1 or -23? Well, the most simplest way to do it might be to just treat one of the bits as the sign bit. So we could choose the MSB to be the sign bit, and if this bit was 1, we could treat the number as a negative number, otherwise we could treat this number as a positive number. So here if we consider integers represented using 3 bits, I have placed all these 8 valuations of 3 bits along a circle, marked in color the most significant bit. The ones marked in red are the ones where the most significant bit is 0, the ones marked in blue are where the most significant bit is 1. So in our notation these would represent positive numbers, these would represent negative numbers, and this is what I would get. So all of the numbers with MSB 0 are positive, and then the black part just gives me the value of the number 0, 1, 2, 3. All of these with MSB 1 are negative, and then the black part of the number of the binary representation just gives me the value of the number, the magnitude of the number, which is 0, 1, 2, 3. So you see that the values represented are increasing this way 0, 1, 2, 3, and also increasing this way -3, -2, -1, 0, and in fact we have 2 representations of 0 here. So this is kind of wasteful, and so what we might want to use is another representation which is called the 2's complement, in which we still consider the MSB to represent the sign of the number, and so in our circle along which we have placed all the valuations of 3 binary digits, we would still have these 4 representing positive numbers, these 4 representing negative numbers. However, we are now going to treat these positive numbers as 0, 1, 2, 3, and instead of these being minus 0, minus 1, minus 2, minus 3, we are going to now consider minus 4, minus 3, minus 2, minus 1. So effectively we are starting from here, continuing to increase minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3. So we have one complete sweep over here in which all the numbers represented increase, and of course finally when we go from here to here, we would go from plus 3 to minus 4, the largest integer represented to the smallest integer represented. So that is the wraparound that must happen. So you see that in this way of representing signed integers, we have been able to represent 8 numbers minus 4 through 3, and there is only one representation of 0. This is also called the 2's complement representation, and one might ask if there is an easy way to figure out, given such a binary sequence, what number does it represent in 2's complement. We could draw the entire circle like we did here and try to figure out what number it represents, but is there an easier way to figure out? It turns out that there is. So you first look at the MSB, and the MSB here is 1, which means the number is a negative number. Then to get the absolute value of the number, you ignore the MSB and look at the rest of it. So in this case it is 0, 111. The first thing you do is flip every bit in this part which you obtain after ignoring the MSB. So 0, 111 with every bit flipped becomes 1, 000. This process is also called taking the ones complement. So 1, 000 is the ones complement of 0, 111, and this, as you would recognize, represents the decimal number 8. And now what we do is we take this number and add 1 to it to get 1001 or the decimal number 9, and this is now called the 2's complement of 0, 111, and this gives you the final absolute value of the number that was represented here. So the absolute value here is 9, the number was a negative number, so 10111 in 2's complement represents minus 9. Now in a C++ program, how do we go about saying that something is going to store integer values? We use this keyword int, which represents the integer data type. I have highlighted the keyword representing the data type in red, and C++ actually allows different kinds of integers. For example, I could have short integers, long integers, unsigned long integers, and what all these different qualifiers do is they tell us how many number of bytes are to be used to store the value of the integer. In a short integer I use 2 bytes, in a standard integer I use 4 bytes, in a long I might use 8 bytes, and they also tell me whether I should treat the integer in 2's complement or not. So all integers, unless explicitly specified otherwise, are signed 2's complement representations. If you specify something as unsigned, then of course it is an unsigned integer. And it is not hard to see that the maximum and minimum values will depend on the number of bytes and on whether you are treating it as a signed or unsigned integer. For example, if I take a standard integer which is signed 4 bytes, then minus 2 raised to 31 is the smallest number that you can represent, and plus 2 raised to 31 minus 1 is the largest number you can represent. Whereas if I take unsigned long which is 8 bytes, I can represent values from 0 through 2 raised to 64 minus 1. In C++, you declare a variable of integer type by putting the type name here int, then putting the variable name mymarks, or you say unsigned short int, that is the type name with the qualifiers and then the variable name. You can also represent constants, integer constants in C++. They could be represented in the decimal notation, which is the usual notation that we always use, a sign followed by digits from 0 to 9. The only thing you have to note is that you cannot start it with a 0 unless you are representing the value 0, because if you do start with a 0, it represents a constant in the octal notation, which is basically base 8 notation. So if I say 0372, it is not the decimal number 372, but it is the octal number 372, and you can work it out yourself what it represents in decimal and in binary. Similarly, I could also use hexadecimal, in which case I would have to prefix 0x, and in hexadecimal, which is basically base 16, I need numbers from 0 to 15, but we only have the numeral 0 to 9, so we use A through F to denote 10 through 15. So if I have a number like this prefixed with 0x, it is a hexadecimal number, and using the usual expansion in base 16 I could figure out what number it is in decimal and what number it is in binary. As a declaration I could say that something is a constant integer. So here this is a constant name scale factor, this is a constant integer, and this is the value of this constant, and when I say constant then the value of this cannot be changed during program execution. So here is a summary of what we have studied today. We have looked at binary representation of integers, conversion to and from decimal, 2's complement representation, and C++ declaration of integers. Thank you.
So that was unsigned integers and signed integers, and now I would like you to answer this question. So it is the same binary string that we saw earlier, 101010, but now I want to treat this as a signed integer. Okay, so I hope everybody has come up with an answer for that. The answers may differ. Now swap it with your neighbor, and in this particular question, in the previous question when we were interpreting 101010 as an unsigned integer, I did not expect any discrepancy between what you wrote and what your neighbor wrote, but in this case I wouldn't be surprised if there are some discrepancies, and both of you may be correct. Okay. So have you swapped with your neighbor and discussed in how many cases are there mismatches? So if there is a pair of students whose answers do not match, for all pairs the answers match, that is a bit disappointing. I was hoping there will be some, because there are two different answers to this question. So how come nobody came up with the other answers? Okay, so let me ask. Yes, can you, the person behind you, yeah. So what is your answer? Pardon me? Minus 22. Yeah. Minus 11. Okay. And your neighbor also got minus 11? Oh, so there is a discrepancy. And have you convinced each other why there is a discrepancy? No, so please try to tell him why you think it's minus 11, and he's going to try to tell you why it's. So somebody here got minus 22, and your neighbor also got minus 22? Minus 22? So anybody got something different from minus 22? Yes? Minus 23. Okay. So we have minus 11, minus 22, minus 23. And your neighbor agrees with you? So who's your neighbor? All three of you got minus 23. Oh, okay. Okay. And what are the results that you got? Minus 23. Oh, so all four of you got minus 23. Okay. So let me ask you, how did you get minus 23? So anybody got minus 23? Just the four of you. Okay, so you are a bit isolated. Okay, so tell us how you got minus 23.
We need to just invert, like 1 will be 0, 0, 1. It will become 0, 1, 0, 1, 0, 1. First of all.
0, 1, 0.
MSP is 1, so the number will be negative.
Okay.
Then we have to invert, so it will be 0, 1, 0, 1, 0, 1.
But where is the last? 0, 1, 0, 1, 0. If you throw out the MSB, there are a total of 6 bits there.
Yes.
If you throw out the MSB, you'll have 5 bits remaining.
It will be 1, 0, 1, 0, 0, 1. Then we need to add 1. So in binary, 1 plus 1 is 11. So 1 will be transferred to the left side. So new number.
No, wait. It's too fast for me. So this one is for a negative number. Does everybody agree with that? This is a negative number. Okay. So now what you are saying is that.
Then we have to throw that MSP.
Then you have to?
Throw that MSP.
We have to throw that away.
Yeah,
okay.
Then we need to invert it. Means 1 to 0 and 0 to 1.
Yes.
The number will become 1, 0, 1, 0, 1.
1, 0, 1, 0, 1.
Yeah.
Okay.
Then we need to add 1.
Yes.
So in binary, 1 plus 1 will be 11. So 1 will be transferred to the left hand side.
No, so you don't need to do it in binary. So whatever 1, 0, 1, 0, 1 you are getting, convert it to decimal, add 1. Okay, so what do you...
So the new number will be 1, 0, 1, 1, 1.
Okay, so So after you throw away the MSB, so the MSB is 1 and the other part is 01010 and you flipped it, so it became what? 10101.
Yeah.
So what is this number in decimal?
This
What is this number in decimal?
So it will be 16 plus
21. Okay. And then you have to add 1 to it.
In the procedure just given, I add 1 to it.
Yeah, we have to add 1 to it. So 21 plus
In the
1.
binary or?
So you mean 21 plus 1 in binary will give you 23 and 21 plus 1 in decimal will give
I am
you...
not asking that. We need to add 1 to that binary number or to...
You just need to add 1 to that number.
After converting decimal?
Answer should be the same. Whether you represent a number in...
11 or 10.
So 21 plus 1 is 22.
So 1 plus 1 in binary is 10 or 11.
Yeah, please let us listen to the argument because this is a common source of mistake. So
1 plus 1 in binary is 10 or 11. I have a doubt in that.
no, so I'm not asking you to add in binary. I'm just saying you get a number, add 1 to it.
I did it.
Add 1. I mean, if you know how to do binary addition, by all means go ahead and do it.
I had the confusion that 1 plus 1 in binary is 11 or 10.
1 plus 1 in binary is 1 0. It is not 10.
That only 1 0 or 1 1. That I had a
No,
confusion.
1 plus 1 is 2, right? So 2 in binary.
In binary, sir. That 1 you need to transfer the left.
No, so let's look at this. 1 plus 1 in binary. No, I mean, so 1 plus 1 in binary is what? Is your question?
0 or 1 1. That I am asking.
So let us answer that. But this is your question. 1 plus 1 is how much in binary?
Yeah.
Right?
Yeah.
Now, you first tell me 1 plus 1 is how much in decimal?
2.
2, right? How do you write 2 in binary?
1 0.
So 1 plus 1 in binary better be 1 0. I mean, we cannot change addition whether we are representing binary or decimal, right? Yeah, so 1 plus 1 is 1 0, but how does that make any difference?
I did it 1 1.
1 1, okay. So you don't need to do, when we said here add 1, this is just add 1, it's as simple as add 1. So you are getting some number here, convert it to decimal, add 1, okay. So you have minus 22 now, okay. So everybody has minus 22, anybody got something different than minus 22? You got something different, okay.
So in the first method which we used, in which there were 2 zeros, the ambiguity was there, plus 0 and minus 0. Using that method, I'm also getting minus 10.
Minus, very good. So did anybody get minus 10? So why were you not raising your hands when I said who all did not get, What? Both answers. Okay, but if I'm asking you, did anybody get something different from minus 22? Because this question actually has 2 answers. I mean, if I just ask you this question, that what is 101010 as a signed integer, what I have not specified, and I was expecting somebody in the class would say, what the hell do you mean? I mean, signed integer, is it the first way of representing signed integers or the second way of representing signed integers? We just discussed 2 ways of representing signed integers. So, and you'll of course get 2 different answers in these 2 ways. So, somebody there got minus 10 using the first way. What is the first way? That you treat this 1 as a sign bit, so it is minus, and then you just treat the rest of it as a normal integer, which is 10. So it's minus 10. But then, that is a wasteful representation. It has 2 ways of representing 0 and all of that. But nevertheless, it's a representation, and we studied that, right? So minus 10 is a correct answer for this if you take this signed representation to be the first representation where you just have a sign bit. But if you take the 2's complement 1, then this is minus 22, right? So there are 2 different answers, minus 10 or minus 22, depending on how you interpret the representation to be. Is it 2's complement or just the sign bit representation? And both of them are correct answers as long as you're clear in your mind why you're getting the answer that you're getting. Okay? Good. So we'll end here today.